Okay,
Yeah.
so yeah, so and then we're gonna
Tell you something.
install the recording.
Did you know that the term gargoyle comes from the Italian word gargoyling on these nuts?
It'd be the worst thing I've ever heard in my life. Gargle on I think you're
There's
supposed to
so
set
many
it
things I
up.
want to say, but I want to keep my job. So
I told you I saw it on TikTok.
Should set them to the You should just video it yourself. Hey, you missed a chance to go viral. You should have videoed yourself. Seriously. Crazy.
Well, I'm going to try.
What is that?
okay.
Did you like my joke?
No, we're back to the death trap called the merry-go-round.
That's right here.
And this is what made you turn you from a child into a playground warrior. That and getting smacked in the face with the dodgeball. Okay, so it's technically a disc. We have it's a mass of about 100 kilograms, radius of 2 meters.
It's pretty cool.
Rotating horizontal plane.
Game that was kind of like that.
Student with mass of 60 kilograms.
It was just like, it was kind of stupid, but I was like, man, this shit was so fun. Like you drive your little boat around it, and like you choose your weapon and you shoot it at it.
Student walks slowly
It
towards
was even time, but it was fun.
The coach like.
Coming into the speed of the system when they reach 0.5 meters from the center. Okay, can we do that?
Yes, we can.
Okay. You should really turn on like a door. Now that show always did bother me because Dora would ask questions and stare at you and cause silence. You get a couple of rocks and the television.
Oh, I love it. My goodness. Oh, maybe a hundred episodes. I didn't. You're like, okay, buddy. Yes.
Okay, so the main thing that we're looking at here.
I'm just like, wow. Like, 2 hours, and I was just like.
Yeah.
It's like, you know,
Yeah.
So this is the idea we're working with. Now is what? Angular momentum. We'll go ahead and remind ourselves. Yeah, we will. Angular momentum is moment of inertia times angular speed. Now,
Yeah.
let's say that we set this up as so we have the initial angular momentum of the disk or the merry-go-round plus the initial angular momentum of the student. And we get the final angular momentum of each one. Okay, so a disk. What is the moment of inertia for a disk? Then 1/2 m r squared. Okay, so that means the angular momentum for a disk is going to become 1/2 r squared. Now, the one student. What is the inertia for the student?
Isn't 2/5, that's hard.
It's just, so what about the angular momentum of a point mass that's rotating around a center that's moving in angular motion around a center point?
Speakers.
So there's.
It's the most basic version of moment of inertia that we've had. M r squared.
So when to
He's on the edge, right?
Yeah. The student just counts as a point mass. Now, the final,
They're number 4 in the nation.
I'm supposed to apologize. Just. She said everybody.
Circle's 5.
No, I'm not saying.
so the disc maintains the same radius. The disc is not changing its size. It's the point mass is moving in. So initially, the student had that full radius of the disc. Then they move into about half a meter. So that's that small r.
But it's.
I think it's one of those situations.
Right.
You didn't.
Still have the mass of the student and the angular speed. I mean, that's still gonna be what it is. What's changing here is the
But it's also.
radius that the point mass is at. Okay, so we are solving for omega prime. Okay, so, well, we're gonna go ahead and flip the equation around.
Party.
Okay,
So it's kind of like,
so then,
I think she's still going because she's got it. That's great. You learn her life story. Right?
so this is where we can start plugging in numbers. I don't really want to plug in all those numbers, they're up in the problem. So I will leave that for you to play with your calculators, because then what you end up getting. Keep in mind, your omega initial is gonna be that 2.0 radians per second that the problem states. Don't worry about what the speed was before the student jumped on. You're just worried about from the time the student jumps on to the time the student reaches half a meter. Now, what is part of the find the change in the system's rotational kinetic energy caused by the movement to R equals half a meter. Well, change in rotational kinetic energy. Sounds like a metal radio. Oh, okay.
Yeah.
Kakarot?
This came. But like.
No, no,
No plan.
you know who Kakarot is, right?
Yes.
It's Goku.
I was gonna say Dragon Ball.
Yeah, Kakarot's Goku.
Is that like?
You wear these One Piece shirts all the time, and you don't know.
All of these.
You have greatly disappointed me.
I know
who Kakarot is?
Yep, Goku.
Yes, Kakarot. I am for small seconds.
So I have like 20 foot in there.
So. Like it's so.
Okay, so what is kinetic energy for rotational motion? And for a moment of inertia, So we have to take into account the moment of inertia of both the disc and the student jumping onto the disc. Okay, so the disc stays the same, that's 1/2 mr squared. The final moment of inertia of the student is mr squared, little r. How does the moment of inertia of the student change when it's like the initial moment of inertia?
Or you know, big R.
Big R.
Wednesday is June.
Okay, so you can go ahead and simplify this if you want to. You can plug in numbers from here. We can plug in numbers. You're going to end up with 920 joules.
Yeah, but we have our June dates. We run every day.
One more letter to go, and then we're done with rotational motion. I know rotational motion's been your favorite part of this semester. Cross products. I'm glad we're gonna get past those torque jokes.
They're not going away.
Figured you would. Find the
We're gonna
work.
find a new joke, whatever you have next.
No, just wait. In the fluids chapter, there's a thing called a manometer, and I had so many jokes I wanted to do. I just can't.
Don't worry, they will figure it
I'll get them.
I did make a meme for it, though. It's probably the worst joke I've ever thought of. Okay, so C,
In which way?
huh?
Worst in which way?
It would make a dad cringe.
Rachel's like, you need to delete that one.
So find the work done on the student as they walk
It's funny.
to R equals 25 meters.
We're tackling it.
So, what is work? Not potential. Changing kinetic energy of the student. The kinetic energy for the disk isn't changing. So we only need to worry about the kinetic energy of the student, which is going to be okay. Half m r squared, r squared. Half m big R squared. Maybe initial squared. Oh, we could say, we could pull out the 1/2 m. R squared. Minus squared. Make it initial squared. And then from there, we just plug in our numbers again. Work done on the student. The negative 355 joules. All right, who's ready to see rotational motion dominate the final exam?
Yay.
Never mind, she's here.
I was like, wow, you weren't kidding.
Hi.
Okay. So, that is angular motion. Now,
So we're done with working?
I hope so, but I'm gonna guess not.
Sometimes you gotta make a little cash on the side. Don't hit the player.
Now, surprisingly, the math for fluids is not that not that difficult. It's more getting the conceptual than anything. Okay. The pressure of a system of fluid. So the average pressure of a system is going to be the force. So you imagine you have an object underneath the fluid. The force is coming in on all sides. So you're looking at pretty much the total force over the surface area as the force is pressing in on. So given that, what do we think the units for pressure is going to be? That's an area is what? Square.
Oh, that's volume.
What is it? So what do you think this equals? A Newton per meter cubed. There you go. Pascal. All right, so Pascal's principle. So imagine you have two pistons. So the work done on piston 1 equals the work done on piston 2, and they both equal E delta V. Okay, so if we say that okay, so if we say that what? Pressure is going to end up equaling 1 over A1.
Yeah.
2 over A2. So we also need to take account of the fact that we think delta V is going to equal. So let's say you have that pressure pushing down on piston 1. Okay? It's going to move through.
What is that, like a 95?
It starts there. Let's say it moves through there. Moves through a distance D. What do you think delta V is going to be? Yeah, so the delta V is going to be the volume of the fluid that's in there.
Yeah.
What do you think that's, how do you think you calculate this?
Distance.
Area times what?
Distance.
Mhm. So we also have delta V equals A1 D1 also equals A2 D2. Because you see how the two containers are connected. So the delta V is going to have to be the same for each of them.
Right.
It's just distance will be less, stuff like that. This is due to the fact that liquid has a unique property that we haven't discussed yet. Why do you think delta V has to be identical? What is it about the liquid that makes sure that the delta V in column 1 equals the delta V in column 2? Think of it this way. Have you ever done a thing where you put the water in the syringes and connect it by a hose and press one syringe? What happens? So you push the other one out. Why?
You can't change the volume there.
Well, you're changing the volume of one, but it equally changes the volume of the other. Equal and opposite.
You
And what
can't
do
lose
we-
volume.
Do you know what the property of fluid is that makes that happen? What happens if you take both syringes and you press it and it won't go? Why?
Equal and opposite reactions.
Fluid is not what? Not compressible.
Okay.
Fluid is not compressible. So that's a lot of what you take into account when we're looking at fluids. Okay, so let's look at word for piston 1. Okay, what is the most basic equation for work? So, well, just work by itself. The very first one we ever learned, force on distance. Distance. Now what I'm gonna do is I'm gonna pull our little trick and I'm gonna do multiply by 1. That's gonna give me
It is a little bit, yeah.
2 weeks. For sure was
that equals P plus V. So also, oh, hang on. Look this way.
I know.
It's that one over here.
I know. This is not.
It's like crack cocaine. Don't be a crack.
Now you notice that we have equations for each piston. Well, why do we not have 1 and 2 on the P and the delta V?
No.
Stays the same.
Yeah, it stays the same. Again, these two chambers are connected, so delta V for one has to be the delta V for the other. And it's a singular fluid, so the pressure of one equals the pressure. That's why you see that the work done on 1 equals the work done on 2 equals P delta V. I thought this one was hilarious.
What is for? I get it.
You're perfect.
M is
You
1,000.
got that?
You have to remind me, M is 1,000.
Yep, you're not.
That is funny. I think it's funny.
Of course, with Roman numerals, if you place one to the left of your. You place fractions. You place them to the right of each other.
Capital M,
Then
the
it's addition. Yeah, this one is an
Like,
M.
what- how would you get it?
Normally it would be capital M, but-
1,000 plus
You what?
1,000.
well,
Plus the
yeah,
4,000.
7,000.
So we're looking at a hydraulic lift.
7,000.
Radius of the smaller piston is 2 centimeters, the radius of the larger piston is 20 centimeters. What is the increase in pressure
7 M's.
caused by a 250
You know,
Newton
it is
force?
the
M's,
rotational
dog,
system.
that's what it would be.
Mhm. So the pressure that we're looking for
No, shut it.
okay?
You can have to lose yourself.
So given the force and the problem, how do we get area of the piston? Yep.
People were just like, instead of names, we're all just different numbers.
So different. I would name 4 years.
That looks like being on
Yeah, but a lot, like, just thinking that's how the world works, we're just, there's a lot more numbers.
well, eventually we'll all have computer chips.
Yes, sir.
Yeah, but will they call me by like my chip number, or will I still have the name?
They probably won't call you anything because you just walk in a place
Like,
and the AI will read your chip.
And like Nebraska.
When
And
it's get my attention, would he say my chip number, or would he have like?
Probably just give leading a device that was.
Just imagine it's like-
Small electric shocks.
No, she went to.
So you guys are high school speed.
Group 7.
So of course, you see this is gonna end in Newton per square meter. So it's Pascal.
Well, I don't talk about any of that stuff.
Someone on check. I know. I'm not going, I haven't looked up when it was.
Part B. If the larger piston moves 5 centimeters, how far does the smaller piston move?
there's no.
Just learned how to pronounce your last name.
Yeah, we do.
After you get back. Cause I'll.
And so what we're interested in,
Yeah, I have to go to sleep.
we'll just call the smaller piston D1 because that's how we started it.
Yeah, cause I'll get a bed.
Yeah, just.
Okay. We have to put a few things in here. What do we do next? Right, so this is gonna be pi R2 squared, 2, pi R1 squared, is 1.
Oh my God.
Straight up.
So, now we can cancel out the pi because we hate putting it on the calculator.
Yeah. There's a stomach over here, just make it. You're supposed to like kill each other.
And
Yeah.
Yeah, that's what.
for someone like me, canceling out the pi. is
Like
not
the
great.
original. It definitely came out.
So it's not the original.
Okay, so
It's I suppose.
I can't see the side of the degree. No, I just know.
Well, here's the thing.
I'm sure.
So you see that the distance that the smaller piston moves is going to be 5 meters.
You know me.
The larger piston moves 5 centimeters, the smaller
It's
piston
just,
moves meters.
it is a nice Lenovo.
You see stuff a lot, you see stuff like this in say like an automotive,
It's kind of slow.
like a mechanic shop a lot. You put the car on the,
It's like,
I
it's
call it
kind
lift.
of not nice.
you notice in
It's slow.
hydraulics that there's moving quite a distance compared to the way the cars are like here.
I'm sure
You get that transfer of energy from a very small piston into a very large piston, you can look at very weight.
Oh, like half, like sure half.
But so far, those are not too bad. Mostly conceptual stuff.
This is.
I feel like I should get a camera.
That'd be a fair idea. Really quick, because it's been bothering me since your Roman numeral joke. There's a clock I've seen in the dentist office in Crawford. It has the Roman numerals, but for 4, it has 4 I's, not IV.
Yeah, that, yeah.
How would you do it with M's like that? Is that still a joke?
Yeah, because in that case, since
Like if
they're
I
all
wanna
the
do
same number,
7,000
since
instead
they're
of,
all the same number, they're gonna add.
yeah,
And usually it's a larger Roman numeral, a smaller Roman numeral, if the smaller one's to the left, then it's a subtraction.
what's the Roman numeral for 10,000? Is there one for 10,000? There should be, right?
Is it 10 M's?
I think there is.
Cause otherwise I'll have to just put 7 M's together.
Because what was it? It's X is
Make
10,
7,000.
E is 5, I is 1. Was it C is 100? Oh.
You do M,
And then L is 500?
like 10 times
Yeah,
10.
what is? I don't remember.
I feel like L is 500,
Yeah, it was 1,000.
M is 1,000.
Okay. The effect of gravity. You just nice
It's
little pressure 1 plus the density. Times the distance
It's
times
like,
gravity.
kill someone real quick.
How do you look at that?
You got M, right? Add some speed ups. Xanax is a very stable drug value.
You'd be surprised how similar fluids and gases are.
It's like a price constant.
Actually, that's how planes work. They like the airfoil essentially turns a gas into a fluid.
See?
When you're dealing with buoyancy.
It's always working. And this game started back in 2020.
Okay, so we have a container with fluid. Now, what we're gonna do is in here, we're going to imagine
Let's.
we're going to imagine a cylinder, okay? It's not actually in here, but we're imagining this, this cylinder of fluid inside the fluid, okay? The cylinder has a surface area A.
Yeah, yeah, it's like Pokemon.
No.
Except.
And it goes to a depth. It starts at one depth and goes B to a deeper depth, okay?
It's like red.
Because this is where you start to take account of how pressure changes
That's what
as
I
you go
mean, it's
deeper,
like
deeper,
eggs and
deeper.
that, it's not really. Well, yeah, there's no moving around a map.
Okay, so-
Check this out.
The mass of the cylinder is going to be its density times its volume. What is the volume of the cylinder? E. So that means now the mass is going to be rho A times D. Okay. And so the force of gravity on this cylinder,
Yeah.
mass times gravity, rho A B G. Now, let's take this cylinder, I'm just gonna.
Computer nerds like. You're a computer nerds.
You're right. What the hell am I making?
He meant that, I think he meant.
So we have the cylinder out here. Let's start taking account of all the forces on
Yeah, but like, you stuff.
I see. I get what you
it.
mean.
Times gravity.
Pretty expensive.
Oh, let's see, then we're gonna have.
I just said.
No, because it's kind of, it's like this one, it's exactly.
I'm guessing.
Well, so let's find. Why did I only do above and below? This is why we use a cylinder. Yeah. No. Yeah, so no matter what, it's a circular outer wall. So the pressure is going to come in at every single angle around that outer wall, canceling all the pressures out going around the cylinder. You just have the pressure from the top and the pressure from the bottom. And we call that pressure 1 and pressure 2 because, of course, different depth, you have different pressures. All right, so.
And the A is just there because we're just accounting what's directly above.
Right, and each band has the same surface area.
Yeah.
So, what do you think we do next since we made ourselves a free body diagram? Some forces.
Yeah, good.
I know, I got it.
Yeah, you do. Force 1,
7,000 some pieces.
force 2,
So that'll be the biggest.
And that's why you got the each.
plus the weight of this cylinder, of this imaginary cylinder of
That
fluid.
AT.
We're in an equilibrium system. So force 1 is minus P1 A, force 2 is plus P2 A, and then minus mg 0. Let's see, so that's gonna be P1A plus P2 A minus A dg.
How do I publish?
Tell me what I did here. Well, I'm gonna put the P2 in plus and positive. What do I do there? What's in equilibrium?
Oh, you just cancel out the A.
Yeah, since A is a part of each one of those, I can just divide it out. And so when we solve this, then we end up at our nice little equation. So the P2 at the deeper depth equals P1 at the higher depth plus rho GD. Now, how does this change? How does this change when the fluid is open to the atmosphere? For which one?
From the top?
So the pressure at any depth can be calculated, if the fluid is open to the atmosphere, it can be calculated how?
Good job right now, actually.
Atmospheric pressure is one of them, which one? Where would your cylinder start? At the top, so that's P1. P1. So at any depth, the pressure, atmospheric pressure, and of course, the rho is the density of your fluid, and you have gravity and the depth that you go to.
Are you saying it's like the cylinder is open on one side or?
No, just imagine the top of the cylinder is at the very top of the fluid.
Oh, not inside of it, like.
Right, so at the top of the fluid, all you have is atmospheric pressure. But generally, the general solution is the cylinder inside the fluid at some place. But then you can change it by moving the cylinder all the way to the very top, where that top area is at the very top of the fluid. And so the only pressure on it at that point is the atmosphere.
I was just asking.
Okay, so. Submarine is constructed so that it can safely withstand a pressure of 1.6 times 10 to the 7 pascals. How deep can this submarine descend if the average density of seawater is 1,025 kilograms per cubic meter? Okay, well, we have our, so which one are we gonna use, P1, P2, or P and P atmosphere? Atmosphere, because we can start from the very top of the list.
Not meeting the right. Just gonna say waiting for me again.
So, in which one of these are we solving from? Distance, how far down can the submarine go? Okay, then I plug in numbers. Your distance is going to end up equaling
No, just bring me this.
1583 what?
Yeah.
Meters. So almost 1.6 kilometers down, and that's the limit of the submarine. Take a few moments and do a short proof of how Pascal's. So Pascal's in the numerator, and then you have, and then you have kilograms per cubic meter times meters per second squared in the denominator. How does that get to meters? Yeah, so that's going to be one of the keys. The Pascal, the Newton per square meter. Well, kilogram, not per meter. Per what? Per second squared. Got to reach back to like chapter 3. Stop drinking your infusion, improve the units.
Yeah, the kilogram, like that's way out there. I really got like, I can,
Out there for what?
out there in my mind, it's pounds of this kilogram. That's where I left these here. The meters, square. And it's like, I remember, learning about it, I'll see each other, even here, that's what's. I was looking at Brandon. Yeah.
Yes.
So like, I mean, I'm always mean guy. Yeah, really nice experience.
I think you'd be surprised at how short this chapter is. No, there's just not a ton in it that we need to. Nope.
We're trying to touch weather, right, or something.
Well, so we're gonna do this one and then we're gonna go into after this one, we're gonna go to sound.
We're good.
And this one in sound should be quite a bit easier than what we've been doing. Did you get to meters? Nice. So what do we have? We start with. So we have Pascals over, when we multiply the units on the bottom together, we're gonna get kilograms. Over meters times seconds squared. And we know that the Pascal is the Newton per square meter. Give us, squared. It's going to give us newtons. Kilogram per second squared. The Newton is the kilogram squared over kilograms per second squared. It gets us to meters. Okay. So. So measuring pressure, and here we have the manometer. I'd never heard of it, like I'm used to the barometer. But you see that the gauge pressure that we end up with is the exact same gauge pressure you remember from your chemistry textbook for the barometer. Rho GD, or in your chemistry textbook, it was Rho GH. So. So what we end up with is we start with, so let's say this is height A. They're both at height A. Then we have heights B and C, okay? So when we go to B and C, pressure B equals the pressure C, origin D. But when we look at the change in the pressure, so imagine one of these sides, so you see the one that says pressure, the other side's open to the atmosphere. So when we change the pressure on that side, delta P, and that delta P is our gauge pressure. And again, this is also the exact same the exact same pressure for a barometer. So since manometer and barometer are both in the chapter, I made the worst joke ever.
Jeez.
Oh, I get it. Advanced.
Huh?
I really like.
So I guess we'll start solving this next time. Because next time I'm gonna let you work on part B for a little bit. It's not difficult, it takes logic.
Yeah, you got-
Like a little.
Yeah.
Granola bar time.
Yeah. That keep it going.
That's fine.